In order theory, a field of mathematics, an incidence algebra is an associative algebra, defined for every locally finite partially ordered set and commutative ring with unity. Definition: a locally finite poset is one for which every closed interval a, b equals x, and xb within it is finite. The members of the incidence algebra are the functions f assigning to I each non-empty interval a, b, a scalar f, which is taken from the ring of scalars, a commutative ring with unity. On this underlying set one defines addition and scalar multiplication pointwise, and multiplication, in the incidence algebra, is a convolution defined by an incidence algebra is finite dimensional if and only if the underlying poset is finite. Related concepts: an incidence algebra is analogous to a group algebra. Indeed, both the group algebra and the incidence algebra are special cases of a category algebra, defined analogously, groups and posets being special kinds of categories. Special elements: the multiplicative identity element of the incidence algebra is the delta function, defined by the zeta function of an incidence algebra as the constant function zeta equals 1 for every interval a, b. Multiplying by zeta is analogous to integration. One can show that zeta is invertible in the incidence algebra, is invertible for every x. The multiplicative inverse of the zeta function is the Mobius function mu. Every value of mu is an integral multiple of 1. In the base ring, the Mobius function can also be defined inductively by the following relation. Multiplying by mu is analogous to differentiation, and is called Mobius inversion. Examples: positive integers ordered by divisibility. The convolution associated to the incidence algebra for intervals 1, n, becomes the Dirichlet convolution, hence the Mobius function is mu equals mu, where the second mu is the classical Mobius function introduced into number theory in the 19th century. Finite subsets of some set E, ordered by inclusion. The Mobius function is whenever S and T are finite subsets of E with St, and Mobius inversion is called the principle of inclusion-exclusion. Geometrically, this is a hypercube. Natural numbers with their usual order. The Mobius function is and Mobius inversion is called the difference operator. Geometrically, this corresponds to the discrete number line. Recall that convolution of sequences corresponds to multiplication of formal power series. The Mobius function corresponds to the sequence of coefficients of the formal power series 1 minus z, and the zeta function in this case corresponds to the sequence of coefficients of the formal power series, which is inverse. The delta function in this incidence algebra similarly corresponds to the formal power series 1. Subgroups of a finite P-group G, ordered by inclusion. The Mobius function is a normal subgroup of an and it is zero otherwise. This is a theorem of Eisner. Finite submultisets of some multiset E, ordered by inclusion. The above three examples can be unified and generalized by considering a multiset E, and finite submultisets S and T of E. The Mobius function is this generalizes the positive integers ordered by divisibility by a positive integer corresponding to its multiset of prime divisors with multiplicity, e.g. 12 corresponds to the multiset. This generalizes the natural numbers with their usual order by a natural number corresponding to a multiset of one underlying element in cardinality equal to that number, e.g. 3 corresponds to the multiset partitions of a set. Partially ordered the set of all partitions of a finite set by saying sigma tau. If sigma is a finer partition than tau, then the Mobius function is where n is the number of blocks in the finer partition sigma, r is the number of blocks in the coarser partition tau, and r is the number of blocks of tau that contain exactly I blocks of sigma. Euler characteristic. A poset is bounded if it has smallest and largest elements, which we call 0 and 1 respectively. The Euler characteristic of a bounded finite poset is mu. The reason for this terminology is the following. If P has a 0 and 1, then mu is the reduced Euler characteristic of the simplicial complex whose faces are chains in P 0, 1. Reduced incidence algebras. Any member of an incidence algebra that assigns the same value to any two intervals that are isomorphic to each other as poses is a member of the reduced incidence algebra. This is a subalgebra of the incidence algebra, and it clearly contains the incidence algebra's identity element and zeta function. Any element of the reduced incidence algebra that is invertible in the larger incidence algebra has its inverse in the reduced incidence algebra. As a consequence, the Mobius function is always a member of the reduced incidence algebra. Reduced incidence algebras shed light on the theory of generating functions, as alluded to in the case of the natural numbers above. Literature. Incidence algebras of locally finite poses were treated in a number of papers of Giancarlo Rota beginning in 1964, and by many later combinatorialists. Rota's 1964 paper was Rota, Giancarlo, on the Foundations of Combinatorial Theory I. Theory of Mobius Functions, Zeitschrift für Wahrscheinlichkeitstheorie und Verwandtungsgebete 2. 340–368, DOI 10.1007, BF 00531932. N. Jacobson, Basic Algebra. I. W. H. Freeman and Co., 1974. See Section 8.6 for a treatment of Mobius functions on poses. Peter Dubalet, Giancarlo Rota and Richard Stanley. On the Foundations of Combinatorics. The Idea of Generating Function, Berkeley SYMP. On Math, Statist, and Proc. 6 Berkeley SYMP. On Math, Statist, and Prob. Volume 2, 267–318. Available online in open access.